All right, now you can go.
Okay, let's get started. So today we're going to be switching gears over to the normal example. We're basically going to be doing everything we just did with the binomial example or the Bernoulli example. It doesn't really matter which way you look at it, if it's Bernoulli or binomial, because some of the xi's and the xi's themselves have all the same information about the parameter that you're estimating p. We'll see a little bit of nuanced differences in this example too, and maybe we can exploit some characteristics like sufficiency, or if we didn't know something was sufficient, if we didn't have knowledge of that, could we still work out the analysis? And the answer is always yes. So sometimes it can just be a little bit swifter. So we're going to be looking at this example, and we're going to be comparing a little bit of classical frequentist thinking, Bayesian thinking through this example. And this example is a little bit annoying because in a lot of ways, not on everything, and I'll try to point out what we don't agree on, but almost everything concerning mu we usually agree on as Bayesians and frequentists or classicists, so lots of beautiful stuff happens with this, and there's a lot of just agreement. If you're doing point null hypothesis testing, there's no agreement. We don't agree with each other, and so we'll be getting into all those issues. I put up a new homework for you. That's right here. And it's basically going to have you work through these normal examples. Also this beta binomial example that you worked through with me in class. And so I'm just going to ask you to do it all. I'm going to have you extend all this to a regression problem where you're given covariance. Turns out all the math is about the same, but you're doing everything with a little bit of linear algebra instead of just scalars. I give you the form of a multivariate thing. We'll probably have to have a couple discussions about this. I tell you what the priors are that you're supposed to be using. I ask you to derive some stuff and compare it to classical estimators like this. And so that should look familiar to you if you've ever fit a line through data or normal equations.
Wasn't that the exam instead inference?
What's that?
The exam instead inference.
Did I ever give you an exam question?
Yeah.
I probably did, yeah. So now I'll tell you how to actually do it. So, yeah, that's right, I did. Or something like it. So, pretty common question though. This pops up all over the place. There's lots of ways of coming up with these equations. We like these equations, so it's worth talking about a couple times. Then there's a problem that I wrote out for you. You'll have to read through a supplement. It's also on the web, so just read through this. There's a supplement that you'll read through. I was reading through a Bayes book that carried through this argument about the prosecutor's fallacy. Maybe you've heard about that, and sometimes I hear about it pop up in the news. And there was a claim that was being made, and I thought, is this entirely clear that it's true? And Peter M. Lee, that wrote out the passage and the problem, is correct, approximately, in his statement, but you have to work out the details. It is about a Stat 101 problem, but you have to fill in some of the probabilities from the passage. So it's always very nice when people give you like, here's a number, 0.95, and you go, well, that's important, I need this thing right here. So be careful with the language, because they're actually telling you probabilities in English phrasings. So it's kind of interesting. And then I asked you to do some transformation problems. So a lot of this class will be transforming random variables. And so I will be including a lecture on transforming random variables to help fill you in. But if you've ever had a probability class, you did this all the time. And so if there's anything you should ever just be good at in your probability class is the dozens of ways to transform random variables that are all equivalent to each other. And so hopefully you understand it all still, but I'll try to catch you back up if it's a little bit rusty. And then I'm going to have you simulate those confidence intervals that we saw in lecture last time, those little jagged things. So you'll do your own simulation stuff. And it fills in all of the details right here, what to do and what to simulate. So if that was murky, what I had actually done, it won't be after this homework. So I've said this will be done by September 18th. So you have 2 weekends to follow through with this. That's a Wednesday as well. Any questions? Okay, great. So lots of normal stuff. Let's get underway with the lecture. So I'm not going to simulate much of this because a lot of us know what normal distributions look like.
We will have a problem-solving session next week, right?
Yeah, we will. And so we will include, I think, both of those problem-solving sessions next week. So Sierra, you can do yours and I can do mine.
Am I a Wednesday or Thursday?
We'll discuss it. We'll figure
Okay.
out. We'll flip a coin.
Nope, I call
So-
Thursday.
Sounds good. So we'll have two and get your feedback on better ways to help you guys out. I think two. Okay, so let's get underway. I like doing all the simulation up front because most people don't know what betas look like. You just see these equations, but when you see it visually, what that density is doing, it's pretty illuminating. I kind of like that. I wish if we could change one thing in Stat 101 classes, we could just simulate likelihoods for people so they can see what the likelihood function is doing. Okay, let's just take a backward step. I'm going to start over on confidence intervals. A lot of us have taken some form of Stat 101, some basic statistics class, and in every one of these classes, they'll teach you this. So, black that out. Okay. Confidence interval. What are they? What's the definition? Somebody help me out. It's a Stat 101 question. I've been in a lot of classes. They would always ask me to define this, and they made sure we knew what the definition was and what it wasn't. And they would always penalize on this until we were finally like, okay, we can just say it, like stop the abuse, and can say it properly. What is this thing? Confidence interval. Tessa, please.
Blank percent of intervals that are constructed in whatever manner you choose are going to contain the true parameter blank percent.
Yeah, so it's this random interval that's covering your true parameter some frequency of times. So it's the probability of your random interval covering the true parameter. And so what's random? Your interval, the bounds on it. And so it's this thing where it's like you have a true parameter, I'll write it down as mu, and you have some procedure for coming up with left and right endpoints. If you had those left and right endpoints, and mu was the thing that generated the data, that generated these two random endpoints, this would have covered. And so if I got more data over and over again, so I go out, I get another set of data, I reconstruct random endpoints, I might get this one, and this one does not cover. So the idea is if you make a 95% confidence interval, you're constructing a procedure that if you did this some great number of times, 95% of your intervals would cover. So the great question is always like, what does that mean? So either it covered or it didn't, and that's what got confusing in the conversation. I'll give you some good news at the end of this conversation. I'll tell you that you can go back to that Stat 101 professor that was abusing you and say, I can say exactly what I want to now. Professor Lehman has said, I can build this interval and I can say, this is the probability that mu lives in here. The probability that mu's in this interval is 95%. And that was the thing that they were always telling you you're not allowed to say. And under a classical framework, that is true. So how do we come up with these endpoints right here? So we come up with a whole bunch of them. Some of them cover, some of them don't. But the intervals are random. It's random because the process is random. Going back out into the population and collecting new data produces a slightly different answer. And so how do we do this? So we might know X bar is sufficient for mu. And I'll keep coming back to those sort of statements and I'll help you to recognize this, but if you get really interested, and you haven't taken a formal inference class, take one. That'll help you to understand mathematically what is all this stuff precisely. But basically, all I need to know is x bar, sum of the xi's, over n. And I'll put an n in here to make you remember that's a function of n. It has something to do with n. N is important here. And so, if I wanted to learn mu, all I need to know is x bar. And it turns out, in any Stat 101 class, they'll teach you this, that the probability that x bar is between some lower bounds and some upper bounds. They'll teach you how to compute this. So you can compute this thing. And I might say, let this be some number alpha. Okay? And they'll teach you in those classes how to come up with these left and right bounds. For shortest intervals, for everything being centered. Normal distributions are symmetric, and I can say something about this thing right here. I can say asymptotically it's normally distributed, so long as variance is exists. And so a lot of people like to make these statements, and it turns out my problem set up that xi's are normal is too strong of a statement. I don't actually need that. It turns out if I had some other distribution generating the data, that if n was really big, x bar would still be normal. Why is that? Because of the central limit theorem. So I'll just remind you, CLT says this is eventually approximately normal. So the CLT doesn't actually say it is normal. It says it gets so close to normal, and they justify rates, and then you test real quickly to see if it's normal enough, and then you proceed. Anyway.
This may be something obvious I'm missing, but do you mean to put a mu inside there instead of an x bar?
So I'm actually putting x bar here. I appreciate your Bayesian empathy right here, but I do mean to put x bar in here. I'm talking about confidence intervals. This thing, what is random to the classicist? To those non-Bayesians. It's only the data. The data is the only thing I can make probability statements about. The data is random, the parameters are fixed. So I'm making a statement about x bar. That's the random bit. And I'm actually writing that down quite intentionally. Turns out I know what these lower bounds are. If the xi's were normally distributed, this just happens. It doesn't matter what n is. If the xi's are not normally distributed, this eventually happens. That I can, if I ended up saying this was 0.95, or approximately, then I might write something down like mu minus 1.96 sigma over root n. And this bound would be mu plus 1.96 sigma over root n. So maybe that clarifies things a little bit, Annie. That this is the precise statement that they usually teach you in Stat 101. Plus or minus 2 standard errors. That's the standard error for x bar. Gives you a 95% interval. And so what's random in this statement? Again, still x bar is the only thing that's random. It's coming from this model. And so here's a term that I introduced last time that you might learn in an inference class, pivoting. And so I'm not going to tell you about pivotal quantities right now, exactly formally, but this is actively pivoting. When we end up rewriting to this probability statement, mu is between x bar minus 1.96 sigma over root n. And it's bounded above by x bar plus 1.96 sigma over root n. So that's the pivot. And so this is what they did way back in the 20s and 30s. They made this move, and they said this is a confidence interval for mu. What is this a random statement about? Still about x bar. We didn't change anything, we just rewrote it. And so the confidence trick that sometimes it's alluded to in history is to get you to think this is a probability statement about mu. Now, this is the thing that all your professors are trying to force you not to do, but everybody thinks about it that way. And so it's like, okay, I've got this interval. Did it cut, is mu in there? I mean, everybody's thinking about it that way all the time, but they tell you, no, it's just this random interval. It either covered or it didn't. It's a 1 or a 0. You know, so it's more of a statement about the statistician. 95% of the time I give people good answers. 5% of people I don't. So it's not a statement about the inference, but about the process. This is a good statistician. I hope I got one of his good answers. So that's kind of what I consider the whole confidence interval thing. So statement not about the analysis, but the statistical control. So this is still random. So this is random. And this is random. A priori to the analysis, I can still say words like that if I'm not a Bayesian. A priori to the analysis, this is a procedure that gives me intervals that cover the truth 95% of the time. So that's what a confidence interval is. But at the end of the day, I get these bounds right here. This lower bound and this upper bound. And somehow that's useful to us. Let's answer the question what a Bayesian does in this whole thing. So at least we know what this thing is. That's a confidence interval. This has a one-to-one relationship with p-values as well. There's a correspondence between those. We'll be getting into that later. But let's just keep this formula in mind. We know what the lower and the upper bound are from the analyses that presumably we've been acquainted with before. Let's see what a Bayesian does. So same problem. Xi comes from a normal distribution. Mu, sigma squared, those are my two parameters. I get n instances, realizations of data. Everything's IID in this problem. And I want to learn mu. So we've made the problem pretty simple. This is known. If you were the non-Bayesian here, you would estimate sigma using probably your standard MLE estimator, plug it in, and that distribution would be t-distributed. That's what would change. So same sort of thing happens here. We'll do that analysis as a Bayesian later on, next week sometime. So for now, the hands of the statistical gods have come down and told us what sigma squared is. Pretty unrealistic, but I can imagine cases for it. Okay, so Bayesian. To be a Bayesian, we need two things. One of them we get for free. We just have to be able to write it down. So the two things are?
Likelihood.
Yeah, okay. So likelihood and prior. So if there's something you can just kind of emphatically say, that's it. You're Bayesian as soon as you say those two words with oomph. So likelihood. What's the likelihood here? It's this thing. I goes from 1 to n. 1 over, I'll just write down the sampling distribution, square root, 2 pi, sigma, e to the minus 1/2 xi minus x bar squared over sigma squared. These are just little normal distributions. So these look like the fxi's given mu. I'll write sigma in there just for notational purposes. It's just a number in our analysis. We don't need to infer it. But this is what it is. I product it up. I plug in the actual data, the xi's. Plug in, oops, this is mu.
Yeah.
Plug in my actual data. I think about this as a function over mu, and it gives me some shape. I could write this down, or I have another choice. I could do this. I could realize x bar is sufficient for mu. X bar is sufficient for mu, bless you. It's actually minimal sufficient. I can't make it any smaller. I can't, here's a less than one-dimensional number. I got to give you something. And so that's the minimal thing I can give you. It has all the information about mu. And I could note x bar's distribution. So I could end up writing down f x bar given mu in sigma squared. This is also a normal distribution. And so this is going to be 1 over square root 2 pi sigma over root n e to the minus 1/2 x bar minus mu squared, sigma squared over n. So x bar is distributed normally with mean mu in variance sigma squared over n. That's why we like using x bar, because it drives down variances. We get more precise about learning mu. Now, if you didn't like that and you didn't know that and you felt disadvantaged, you could work with this. And it turns out this is proportional to that as a function of mu. And you could work that through. And so you could see that the only numbers that popped up next to mu in this whole equation, once you expanded the square, were x bar. X bar is the only control on mu. And so, or you could write it down like this and just know it. But again, these two things are proportional to each other. I'll leave it as an exercise for you to do. If you want me to do those things in a review session, you weren't able to successfully show that, I'd be happy to show you that. That'd be a good warm-up. Okay, so I've got likelihood. I think I understand the nature of my parameter too. So this parameter right here, mu, shifts the distribution for x bar around. It's a shift parameter. It shifts that distribution, and we all know that. Slides the normal distribution to the left or to the right. So I need a prior. I probably want to understand what the nature of that parameter is. So I'm always going to tell you that. You can't just come up to me and say, what's a good prior for gamma? And you don't tell me anything about gamma. How am I supposed to answer that? So what prior would you choose?
Normal.
Help me out.
Maybe standard normal?
Uniform. So heard that. Normal.
Standard normal.
Standard normal. Uniform. So good choice. Turns out normal is conjugate here. So let's start with the normal case, and then we'll move into the uniform case. Because the uniform case is a subset of the normal case, it turns out. It's a limit of it. So the conjugate prior is normal. With some parameter, mu naught and sigma naught squared. So if you're going to actually use this, you need to specify. And so in my class where it's just all notation and it's just an algebra problem, whatever. If it really means something to you, you got to be ready to say, a priori, I think the mean is this number. How uncertain I am about it is dictated by this thing. And so, just as a prelude, if I took this thing and I limited it out to infinity, that reduces to the uniform case, the improper uniform. You might question, what is that? Because I know that's not a probability distribution. It can't be normalized. So we need to talk about all of those things. Just as quick glimpse into the future, it's a good idea to do all of that. And a lot of your priors on non-compact spaces, unbounded things like mu, turn out that you want to give a prior that can't be normalized quite often, unless you knew something about the truth. Come back around to that later in this class. Let's just leave these in as notation right now. So mu naught and sigma naught. How do I know that this model right here has a normal conjugate prior for mu? Well, it turns out this is e to the minus mu squared, some quadratic form. Prior has the exact same form, and I know that when I multiply those two forms together, I preserve that form. And so how do I know all of that? I guess I've multiplied exponential things, and I've seen it done, and I can see the calculation carrying through. And I can notice that the resultant thing, e to the minus quadratic form, is Gaussian, some Gaussian. So everything is Gaussian. And in this case, because the sampling distribution is also Gaussian, and I'll say this is self-conjugate. If you look into the book, they'll define it that way. I've never heard anybody use that term outside of the classroom. Okay, so conjugate is just conjugate. Is it interesting that it's self-conjugate? There are interesting theoretical things that happen in those models. Everything is simpler, as you can imagine.
So is self-conjugate just the likelihood prior and posterior all at the same time?
You got it. Okay. So let's just write all this down. So the posterior, that's what we're after. I'm conditioning on x bar. I'm also going to remind you we know sigma squared. We'll leave that in as notation. So I like it, little reminders all the way through. I get to condition on that knowledge. And so what is this thing? This is going to be proportional to the likelihood given x bar. And I'll condition on sigma squared times my prior on mu. Now, I want to be perfectly formal about this. So, there's no conditioning on x bar over here. The only conditioning on x bar happens through the likelihood. There are people that will pour data into their priors, and we'll talk about that later. We'll talk about what it is to be a correct empirical Bayesian, where you can actually do something good, or a very misleading empirical Bayesian. So, but for now, we're going to assume the prior really is prior ignorance or information, and this data never goes inside of here. We'll change that towards the end of class in some applications. But if I want this thing to look like, so let's just write this down again. This looks like this, fx bar given mu in sigma squared. If you prefer looking at it like that, and I multiply mu into this, is that this equation right here? Keep in mind it's not normalized correctly. What I need to do is I need to convince myself that this is independent of sigma squared to do it, that I don't use any information on sigma squared. So if I were staring at this equation, somebody told me this multiplying to that was equal to that, I would say, okay, you have an assumption about conditional independence of sigma squared. So technically I should be writing down this. But my prior isn't going to use any information about sigma squared. So why? Well, let me just imagine a case. Let's say my variance is 10. Does that help you to know my mean? Does it? If I gave you data, it would. And so those two things can be used together. But without data, it's not helpful. And so I'm just going to remove this from the notation. No sigma squared in there. Because I'm not going to use it. I'm just going to pick these numbers.
So how come if sigma squared is known in the prior, we didn't change anything?
I'm just giving you an intuitive mindset. Variance is 10. What do you think the mean is? Didn't help you. A priori, no information there. So I do like to follow the notation, make sure I understand the probability statement, what I'm conditioning on. And if I drop something from the notation, I'm implying conditional independencies. And so I do like to write out the explicit notation. And if I wrote this all out like this, I'd go, why isn't there a sigma squared here? What most people will do in this analysis and what your book will do is they'll cut this out of all of the notations. Sigma squared, I've given it to you, let's not talk about it. It gets a little confusing, however, if I marginalize sigma squared out of the analysis. The notation starts to look exactly the same, but it means totally different things. So let's be careful, at least talk about the notation. We can get looser with it as long as we all know what we're talking about. And so now I've just got my prior that I need to write down. So this is just an algebra problem. This whole thing is just going to look like this. I'm going to go back to using x bar is sufficient instead of working through the product, although it all worked out exactly the same. You can verify that. So e to the minus 1/2 x bar minus mu squared over sigma squared over n. And I've gotten rid of my normalizing constants right here. So I've gotten rid of the 1 over 2 pi square root sigma over root n. I'm going to pretend like I didn't even write it down. Why? Because I'm just setting this all up to proportionality. If it doesn't include a mu or the data, I don't care. Those are the things I'm after. And then we've got the prior. E to the minus 1/2 mu minus mu naught squared over sigma naught squared. That's it. And I didn't write down its normalizing constants either, because I'm going to be able to know at the end what the normalizing constant is, because I know what normals look like. So this conjugacy thing is great if you know about the distribution, because it won't require you to keep track of any of your normalizing constants or solve that integral in the denominator at the end of the day. If you want to, you can give it a shot. So this is going to be equal to e to the minus 1/2. I'm just going to add the exponent terms, factor out the minus 1/2. I've got an x bar squared minus 2 mu x bar plus mu squared. And then I've got mu squared minus 2 mu naught plus mu naught squared. And this is all over sigma naught squared. And I can't forget about the sigma squared over n over here. So just expanding the square is all I've done. I want you to appreciate this, but I can factor this thing out right here. So I'm going to get rid of that, and I'm going to just multiply it in right here. E to the minus 1/2 x bar squared over sigma squared over n. So this is equivalent, if I get rid of that x bar right here, I've just factored it outside of everything. This has nothing to do with mu. So there's no mu there. So I don't even have to pay attention to it because it's not influencing the shape of mu. This is a posterior distribution on mu. That's what I care about. So that term isn't helping me at all. Keep in mind, as soon as I wrote down up to proportionality over here, I couldn't get away from it. I'd have to actually explicitly solve the integration in the denominator. To do that, we're not going to do that. For the same reasons, I can factor this thing out as well. That doesn't have anything to do with mu, that just factors out. And so I'm left with two pieces that have a linear term in front of them and a quadratic term. There's only those two terms, the quadratic term and the linear term. And so let's simplify this just a little bit. This is going to be proportional to. My mu is what we're working on. I've conditioned this on x bar. This is proportional to e to the minus 1/2. I've got a mu squared term in here. And I've got two things that go in there. I've got a minus 2 mu term, and I've got two things that go in there. Contribution from the likelihood and the prior. So the contribution from the likelihood is going to be x bar. So if I just look back here, oops, no x bar. So the mu squared term just gets factorized out. It's just the variance term. So it's going to be 1 over sigma squared over n. Similarly, the contribution from the prior is going to be that. Now let's look at the minus 2 linear terms. This is going to have a contribution from x bar right here over sigma squared over n. And this is going to have mu naught contribution from the prior over sigma naught squared. And so we've done a little bit of algebra, but it really is just this same equation. Likelihood times prior. I'm interested in understanding this as a function of mu. I happen to know what that is. It's a Gaussian. So let me make you a promise. Anytime you ever see a distribution and it's e to the minus some quadratic form, that's Gaussian distribution. That is what Gaussians are. And so sometimes we write them real neatly with the normalizing constants and place the mean and the variance in places that you can recognize very easily. And this isn't one such case. It hasn't been normalized. And the question is can you recognize the mean and the variance? So this is a Gaussian. Normal. But what's the expectation? And I'll write it down this way. E mu given x bar. That's the posterior expectation. And variance mu given x bar. That's notation for the posterior variance.
I'm completing the square with you, right?
Yeah, so Christina has a tool, and she says, complete the square. You can figure it out, put it into a perfect square, get rid of everything, and so it's just an algebra problem. And we could do that for the next 20 minutes.
2 times this, and you divide it by.
Right, so we might need to remember what that formula is and rederive it, but you know, if you've taken sophomore algebra lately, you're quick at this stuff. And you can rederive it, and that's all fine, and Christina would be happy to show you how to do that. I'm going to show you something different. So I'm going to show you the backwards thing. And just to appease Christina, in about a week or two, I'll complete the square exactly once in this class, and that's the only time I'm going to do it. But I'm going to show you something else for this problem, expanding the square. So here's just a side note. The side notes about normals. So consider a distribution. Let z be normally distributed, and I'll put the typical parameters in there. Mu and sigma squared. Okay, so this is a side note. These aren't the same mu and sigma squareds in this problem, although they represent the same mu and sigma squared. It's just a different problem. Z is my random variable here. So that's my random variable. So I know this thing looks like this. So I know the density, Pz, given mu and sigma squared, turns out to be this thing, e to the minus 1/2 mu minus z, z minus mu. Keep this like you usually see it. So it's just written out that way, and if somebody showed this to you and didn't even tell you what mu and sigma squared were, you'd go, hey, that's the mean of the distribution. It shows up in that place that centers the distribution. I'm used to recognizing that. So instead of writing it out that way, I'm just going to look at the kernel of the distribution. This is the kernel. Tells me everything I need to know to figure out all the rest of it. Normalizing constant. It has all the relevant parameters associated with the random variable that can't be factorized away. So that's what we call the kernel. So I'm going to look at that thing, and I'm going to rewrite it as e to the minus 1/2 z squared over sigma squared minus 2z mu over sigma squared minus, this one's plus, mu squared over sigma squared. Christina can tell you that is the completion of the squared term we're looking for. And so if I can isolate mu and sigma specifically, I can form that term. I'm just going to show you how to recognize it real quickly. How do I recognize where the variance is in this equation? This doesn't help me at all because it's tangled up with mu. Can't quite tell right here because it's tangled up with mu. But right here, if I factorize the minus 1/2 out, all I have is the inverse of the variance. So the quadratic term is multiplied by the inverse variance. So that lets me instantly recognize the variance in this equation. What's the variance for the posterior? It's the inverse of that. How do I get the mean? Well, I take whatever variance I just found and I multiply it by the -2 linear terms. So I go to the -2 linear term. Keep in mind -1/2 is always factorized out already. And then I multiply the variance that I just found and it isolates the mean. So let's do that. So that's how I do this problem. Or you could complete the square. I'm just doing it backwards and untangling everything along the way. I think it saves time, but lots of ways to solve problems. Exactly the same algebra in disguise. So the variance of mu given x bar is equal to quadratic terms multiplier inverted. So that's going to look like this. 1 over sigma squared over n plus 1 over sigma naught squared inverted. So the inverse variance is add, and then it gets inverted again to get the overall variance of the posterior. We'll look at this formula in a minute. I think it's really neat what's happening. There are other ways that you can write this down. The expectation, how do I get it? I just take the thing that I just found and I multiply it into the -2 linear terms, which we've isolated. And that's going to knock out the variance right there. You'll just have your posterior mean. So that's going to be x bar over sigma squared over n plus mu naught sigma naught squared times this thing. 1 over sigma squared over n plus 1 over sigma naught squared inverted.
It can be written as the product of the letters divided by the sum of them, right?
Could be written that way. I like this way. And I understand that there's good ways to look at this formula. Let me tell you what I see when I see it this way. I see a weighted average. So this is just a weighted average. It's a weighted average of x bar in mu naught. So weighted average of x bar, this is data, and mu naught, your prior beliefs. So your prior anchoring to the problem. This can be a very good idea, and people do this. Might have to talk about it if I don't know a good mu naught, okay? But it's a superposition between those. I'm weighting by the inverse of the variance. And so if the variance is very, very small, I'm putting a lot of weight on it. Why? Because I'm certain about it. And so that's kind of a nice weighted average form. And you'll see people use this, and they'll come up with it from different lines of thinking that I need to like anchor my solution. What's the right way? Well, here's a mathematical justification for weighting by the inverse variance, please. And so, and this is just a normalizing constant for that weighting average. And that's what it is. And so I think that's really cool. Some of you had said something about a uniform prior, just uniform across the whole space. Let's see what happens. Turns out we've already done all the important math. So some suggested to use, and I'll interpret the suggestion is this. So my pi mu is going to be proportional to a constant. Okay, for mu between minus infinity to infinity. So I'm writing it down in terms of proportionality. What we're really explaining is uniform behavior. It's flat over the whole thing. So that's what the constant means. Most people don't like just writing down arbitrary constants, and so they'll pick a convenient one. Write it down as proportional to 1. Now, that's not a normalized distribution. If you go to try to normalize this distribution, you're going to recognize that the thing you need to divide by is infinity, which is going to knock out all of the mass. So this can't be normalized. The scales go on forever. There's infinite mass under it. If that doesn't bother you for now, let's just entertain usage of this prior. Think about where it's placing mass equally everywhere. Think about the nature of the parameter mu. It could be anything. And so it's kind of specifying an equal opportunity for that mu to be anything before I see the data. That makes some sense. And so this is equivalent to my normal distribution, mu, being normally distributed. Give myself a little bit of room. Mu naught, sigma naught squared, where I take the limit, sigma naught squared, and I drive it out to infinity. So think about what normals look like. It's going to look like that. They're centered right here, mu naught, sigma naught, the distance to the inflection point. If this gets bigger, this thing starts to flatten out. Start to flatten out even more. And eventually you'll make this surface as flat as you would like. Now if it bothers you to actually make it totally flat, you can make this arbitrarily large. And you'll have the same computational impacts. And so philosophically you're disturbed and about to multiply by something that can't be normalized. Make that thing 1 trillion, something just massive. You'll feel better for now. And so I'm just taking the limit of this. And so to do the uniform analysis, which is the limit of the conjugate analysis, all I have to do is take these equations and take sigma naught and blow it out to infinity and see what happens. So under I mu uniform, that's the way most people will write that, i.e. sigma naught squared goes out to infinity. We're going to come up with a variance for mu given x bar. And very conveniently, when I did that out to infinity, mu naught didn't have any meaning anymore. And so I didn't even have to touch mu naught because it's the centering of a perfectly flat thing that slides back and forth as much as you want, and you can't tell the difference. There is no center. This thing is just going to be 1 over sigma squared over n inverted, which is just sigma squared over n. Infinity, that thing's 0, get rid of it. I can do the same thing real quickly. This thing is going to get blown out to 0, that thing is 0, and so all I'm left with is x bar over sigma squared over n times 1 over sigma squared over n inverted, which is equal to x bar.
You get the exact same thing.
You get an answer that should be intuitive.
Yeah, you're multiplying by 1.
So let's look at our posterior distribution that we've gotten under the uniform prior. Our posterior distribution, mu given x bar, is normally distributed, centered at x bar, with variance sigma squared over n. So the credible interval the symmetric one, the one that has most mass, the one that is shortest. There's no reason not to pick this one in this case. Where I just take off 2.5%. 2.5%. This credible interval is going to be this. So what am I going to do to do this? This thing is centered at x bar. And so I'm just going to go 2 SDs out. And so my credible interval for mu is x bar minus 1.96 sigma over root n, because this is a normal distribution. I know how to collect 95% of my mass. x bar plus 1.96 sigma over root n. So under the flat prior, the Bayesian concludes exactly what the old frequentist did. We come up with the same interval in two different interpretations. This has optimal coverage properties. Bayesian still has it. And they get to interpret mu inside the interval. So now you are equipped to go back to your teacher and say, actually, I want my 3 points back. What I didn't tell you is I was operating as a Bayesian. They're not going to give you the points back, obviously. But you get the point that sometimes we agree and sometimes we disagree on things. I want to talk about this problem a little bit more, how the one-sided p-value analysis corresponds between the frequentist and the Bayesian. It turns out they wildly correspond, and for the two-sided thing, the Sharp test, they totally don't correspond. So there's some differences. We're going to have to wait for a little while to understand those reasons. I want to do some inference on sigma squared and talk about what if we didn't know sigma squared, what do we do? Do we still agree or do we disagree? And it depends. But right now we're feeling pretty good about things. I want to point to why this is. Think about in the likelihood function. The parameter and the data x bar and mu play symmetric roles in the likelihood function. I can interchange them, has the same shape of the curve, it's just kind of shifting it around. There's something about that is saying that the inverse analysis, the Bayesian analysis, is going to have identical properties so long as my prior isn't playing an impact, and I use this flat prior. So there's reasons why the Bayesian and the classicist agree on this problem that they will not agree on other problems if you don't have that symmetry. Let's come back next time and do a few more problems. Thanks, guys. Have a great weekend.